In this video, we're going to talk about domain and range. We're going to talk about rate of change, intercepts, and different representations of functions. So I want to start out by talking about domain and range. This is an important concept for you to kind of understand how the two sets are related, what domain and range mean, how they're related to each other, and it's also part of the definition of function as well. So the domain of a function is simply the set of all the x values that make up that function. So it's all the inputs. And the range is the set of all the y values that make up a function, or it's all the outputs. Alright, so let's look at an example here. If this is the function 2, 4, 3, 5, 4, 6, 5, 7, and 6, 8, those are the ordered pairs that make up this function. Let's list the domain and range. Okay, now since the domain and range are both a set of numbers, we're going to use this brace. The domain would simply be 2, 3, 4, 5, and 6. The range is 4, 5, 6, 7, and 8. Okay, so the domain is the set of x values, or the inputs. That would be these. The range is the set of y values, or the outputs, and that would be these. Okay, now I want to talk about rate of change. I want to talk about different representations of a function. There are three main ways to represent a function. Okay, we can use an equation, which you've seen a lot of. We can make a table, which we just saw an example of on the previous screen, or you can make a graph. And all three of those are ways to represent a function. So if we look at this screen here, we can see that there are those three things represented here. We have the equation here, y equals 3x minus 2. That is one way to represent a function. It is describing how x and y relate to each other. Y is equal to 3 times the x value minus 2. And there's that relationship that stays constant. Okay, so for example, if x is negative 3, if you look at this table, if x is negative 3, then y becomes negative 11. Okay, and I got that by plugging a negative 3 in for x. So 3 times negative 3 would be negative 9, minus 2 would be negative 11. If x is negative 2, then I have negative 8. If x is negative 1, I have negative 5. You should be able to fill this out really easily now because of two things. And this is where this rate of change idea comes in. Okay, the rate of change in this problem for this function is 3. And I know that a couple different ways. First way is that right here, from negative 11 to negative 8, I'm going to add 3 to get the next number. And that happens here as well. That's going to happen the next time and the next time, all the way down forever. So negative 5 plus 3 is negative 2. If I add 3, I get 1, and then 4, and then 7. Okay, so it's plus 3 all the way down. The rate of change is also represented in this equation as the number in front of x. It's the coefficient of x. Now be careful, because that's not always true. It's only true if the equation is in this form, where y is by itself, and the x term and the constant are over on the right. If the equation is not in that form, then you can't say that's the case. Okay. Now also, you'll see that in the line, the rate of change is 3, because every time I go over one x value, I go up 3 numbers. Okay, so this was from 1 to 2. I went over 1, and the graph goes up 3. It went from here to here, so from 1 to 4. So this rate of change 3 is represented there as well. It's the steepness of the line. If I went over 1 and went up 4, the line would be even more steep. So the slope, this rate of change, indicates the steepness of a line. So on the graph, it's the steepness of the line. In the equation, it's the multiplier for x. In the table, it's the difference between y values, difference between the output values. So once you have this negative 2, which is really kind of like a starting point, okay, and you'll notice that the negative 2 is right here, and we'll talk more about that later. That's a starting point, and from there, everything is 3 units away. So if I go down the table, it's plus 3. If I go up the table from negative 2, if I take away 3, I get negative 5, then negative 8, then negative 11. Okay, so let's look at this again. Another one like it. Fill in the table, graph the function, state the rate of change, and find the x and y intercept. Okay, so the function is y equals negative 2x plus 1. So if I put a negative 3 in for x, that gives me 7. So I can go back to -3 and plot 7, except the graph doesn't go that high. So I'm going to go to the next value. -2. Now the rate of change is -2, so I should get 5 right here because the rate of change here is -2. -2 plugged in, I get 4 plus 1 is 5. So that would be 3 and then 1 and then -1, -3, and -5. So these are points that I can plot now. -3, 7 is off the graph, or at least off of the graph that we have. -2, 5, I can plot approximately up here. Might not quite be 5. -1, 3 is right here. And then 0, 1 is right here. 1, -1 is right here. 2, -3, and then the other one's going to be off the graph as well. So this is approximately the graph of this function. Okay, so we have the equation, the table, the graph, all representations of this function. The rate of change, or the slope, is -2. You can see that here. It goes down by 2 every time. You can see it here. And you can see it on the graph if you went from this point over to this point. Every time I go down 2, I'm going over 1. Slope also can be thought of as a rate of change and as rise over run. So if I divide the rise, or the vertical distance between these 2 points, by the horizontal, or the run, -2 over 1 is -2. And that gives me the slope as well.